Okay, I think we can begin. So welcome everybody to the public licentiate defense for Sahar Tahvili, who has been working at 6 Swedish ICT Västerås here here downtown in Skrapan, and has also been a PhD student here at IDT here at Mälardalen University. So the title of the thesis is An Online Decision Support System for Integration Test Selection. My name is Marcus Bolin. I am the main advisor. I will also be the chairman of this session. And the faculty examiner is adjunct professor Mattias Nyberg from Scania and KTH, Royal Institute of Technology. Professor Mattias Nyberg has over 80 scientific publications, and of which more than 20 are in journal publications, so he's highly qualified for being the faculty examiner. We also have the grading committee, which consists of Professor Mohammad Reza Mousavi from Halmstad University and senior lecturer Eva Torin from Mälardalen University here as well. The advisors has been me, Professor Daniel Sundmark, Dr. Stig Larsson from SIX, and Dr. Wasif Afzal from Mälardalen University. The proceedings will be as follows. First, the respondent, Sahar, will present her thesis. Then, the opponent will lead a discussion on the thesis together with the respondent. And during that session, we as advisors are not allowed to participate. After that, the grading committee, we open up for questions from the grading committee. And finally, after that, the audience is also invited to ask questions. And traditionally, during this part of the defense, the advisors can also participate and clarify some things if that is needed. After this, the grading committee, I will close the open part of this session, and then the grading committee will meet in private and discuss the merits of the thesis. And finally, the chairman of the grading committee will announce the decision for the committee in Java, the coffee room at IDT, where I hope Sahar will show the way, so you can wait there during the discussions. Yeah. Okay, and with that, I open up for Sahar to present her thesis.
Thank you very much. Welcome to my licentiate presentation. My name is Sahar Tahvili. I'm a researcher at 6 Swedish Institute of Computer Science and also industrial PhD student at Mälardalen University. Today, during this talk, I'm going to cover and present a part of our research project, which is an industrial research project with a close collaboration with different industry in Sweden. And we work with Bombardier Transportation to get case studies, and we analyze this data from Bombardier. The topic of my licentiate thesis is a decision support system for integration test selection. Today, I'm going to cover the following points. First, background and introduction. What is software testing actually? And some motivation, why we need to have software testing today. Second, I'm going to present our research question that we solve in this project. And I'm going to present our contribution as well, and some limitation that we have in this project, and the research methodology that we use in this project. And I'm going to close and conclude my presentation with some results and conclusion. So let's start with some introduction. What is software testing? According to the IEEE standard definition of software testing is a process of analyzing a system under test with the goal to detect and identify the hidden faults in the system. You never know, and there is no guarantee that you can detect all hidden faults in the system. But you have this process, and you try to solve this problem before you release a product to the market. But what happened if we haven't this process? Today. From the beginning, we have different examples. For example, Challenger, we have Ariane 5, we have Trace 25 in different domain, and as a newest example, we have Galaxy Note 7, which is not a software testing problem, but it still is a testing problem. So you know if you are going to remove, or if you haven't a very mature process for the testing, what would happen? To do software testing, you need to have an artifact, which calls test cases. We can refer again to the IEEE standard for definition of test case. A test case is a set of some action and some expected reaction. And the result for a test case is pass or fail. When you got pass answer for a test case, you are done with your task. It means there is no bug in the system. But when you get fail as an answer for your test case, you need to re-execute this test case, and it means there is a bug in the system, and you need to do the debugging process or solve the problem. A set of test cases called test suite, and there is different level for testing today. Unit testing, when you just test one component. Integration testing, when you are trying to combine more than one component with each other, and you are going to test the interfaces between these two components. This process calls integration testing, and we are working in this project with integration testing. Here I have an example for a test case. As I said before, there is a set of action, different steps, action, and you have some expected reactions. And here you have results. So in this example, which is a manual test case written in natural language in English, you got pass answer for this test case and you're done. So there's no bug in the system in this example. The required number of test cases that you need to test a system under test would be very large. For example, for one of the projects that we analyzed in Zefiro at Bombardier is a Zefiro Italy for a high-speed train. The number of test cases for train control management system and just in integration testing level is more than 4,500 test cases. So it's quite large. So why you need to prioritize test cases? So here comes optimization problem. Why you are not able to execute all design and generated test cases? Why you need to have an order? First of all, you generate so many test cases, you have so many test cases, but you have always limitation in your resource or you have deadline. So you are not able to execute all of them. And second, earlier fault detection. When you have an order for execution, you are able to detect the hidden faults in the system earlier and earlier. This motivation opens two hot topics in software testing: test case selection and test case prioritization. We use the definition proposed by Harman and Yu for test case selection. Test case selection means you are going to select a subset of generated test cases for execution. Assume this situation. You have a product. You change just a part of this product. It's not an optimal decision to execute all design test cases. You need just to select a subset of design test cases which can cover this part that you have already changed. And test case selection works with scheduling and ordering test cases before execution. And there is different goals for test case prioritization. I explained before, is earlier fault detection and better using of testing resources. During our research, we identified the initial problem, test case selection and prioritization, as a multi-criteria decision-making problem. We use historical data, we use databases, we interviewed different engineers and testers at Bombardier Transportation, and we identified this problem as a multi-criteria problem, which means there is more than one parameter, one criteria that you need to take care about that per time. You are not able to select test cases just by one criteria. You are able, but it's not an optimal decision. So what is the criteria that we have in the testing process? We identified this set of criteria, but this problem is not limited to this criteria. You are able to remove or add new criteria to this list. The criteria that we have identified in this project is dependency, which is the most critical criteria for us. When we are talking about integration testing, it makes sense when you are combining two components and you are trying to test the interface between two components. The dependency between components and the dependency between test cases is most important things that you have. Time efficiency. What is the required time for execution? Cost efficiency is another factor, and there is a direct relationship between cost efficiency and time efficiency. Requirement coverage. How many requirements you are able to cover by execution, by executing just one test case. Fault failure probability. What is the probability of detecting a fault in the system by executing one test case? For using multi-criteria decision making, you need to have a set of alternatives as well. So in this project, in this problem, alternatives is test cases. We have test cases as alternatives, we have a set of criteria, and in the next step, we need just to measure the effect of every single criteria on the test cases, which is not an easy task. Sometimes you have sharp value for test cases. For example, for requirement coverage, you are able to count how many requirements you are going to cover by executing one test case. But how about the complexity? You are not able to answer this question with a sharp value. But you can compare two different systems with each other, and you can answer this question with a set of linguistic variables, which cause fuzzification. So we redefine the initial problem in a fuzzy environment, and we send a set of questionnaires to the testers and engineers at Bombardier with some linguistic variable. The boundary for linguistic variable in this problem is between very low and very high, but you can change it. And if you just answer, for example, what is the complexity for a system, what is the functionality, how functionality is important for you, and what is the time efficiency with some linguistic variable, with, for example, how or low or high, we can prioritize these cases. As a last step, you need to utilize just multi-criteria decision-making techniques, and it depends on you. There's different methods. We use AHP, analytical hierarchy process, or TOPSIS, VCORE, and there's a set of the, methods that you're able to use. Here I have a better example. Assume this situation, you design 10 test cases, and you have a deadline or you have limitation in your resources, and you're able just to execute 6 test cases. So which of these test cases should be executed first? According to our calculation, by using AHP technique, we got some weight, some value for test cases, and we prioritize test cases with this set, and we propose these 6 test cases as the best candidates for execution. In another situation, after executing 8 test cases, you detect all expected hidden faults in the system with 99.5% fault detection. You are not able to reach 200 by executing these 2 last test cases. Just in this example, these 2 last test cases are redundant test cases. If you are going to reach 200, you need to generate new test cases. You are not able to reach 200 with these 2 here. So research question. By using this information, we categorized and classified our research with 3 main research questions. First, how does the usage of a decision support system improve testing process, integration testing process? Second, how the dependency information between test cases with use of other multi-criteria in the system can improve the integration testing process. As a last research question, under which condition and how we can have a positive value for return on investment by using our decision support system. The main contribution of our work is this figure. Here is a design of our decision support system for test case selection and prioritization in integration testing level. We applied our decision support system in the different industrial case studies, and we classified the decision support system with 7 different steps. In step 1, you have a pool for new generated test cases. Different colors for test cases here in step 1 represent different shape of dependency between test cases. You have new test cases which come continuously to this pool. In step 2, you need to use some learning algorithm for getting information about different criteria and measure the effect of criteria on test cases. Still, you have no order for test cases today. we solve this problem manually. But in the future, we are going to use some natural language processes, algorithm, and machine learning techniques to solve this problem automatically. In step 3, we send a set of test cases for prioritization. So we are going to use different methods in this technique, and we are going to prioritize and send a set of prioritized test cases for first execution in number 4. After first execution, you are able to get pass or fail answer for test cases. You need to remove pass test cases from the system, and you are going to send the fail test cases for troubleshooting process in step 5. And here we have another optimization problem. We are working with this problem right now. What is the best decision for execution 2? Are you going to re-execute already failed test cases, or you are going to take a new generated test cases from pool? We are working with this problem now. And we are going to monitor the whole testing process with some indicator like fault failure rate. And we are going to continue this process until there is no failed test cases in the system. As I said before, we applied our decision support system in 3 different industrial case studies at Bombardier Transportation, and we almost published 1 paper per step for our prototype, and we presented our papers in the different conferences. In one of our papers, which is about dynamic test case selection and redundancy avoidance based on test case dependency, we presented this paper in ICST conference this year in USA, and we identified some dependency between test cases, which calls result dependency. Assume you have test case B and test case A. Test case B depends on test case A. We claim if you get fail answer for test case A, you have no chance to get pass answer for test case B. And you need to avoid execution for test case B. We also proposed dependency degree between test cases, and our claim is per time you need to execute test cases which has a minimum dependency degree. If you're executing test cases with a minimum dependency degree, you are able to save more time and testing resources. Here we have an example. These test cases are for a project at Bombardier Transportation, and we checked and we monitored the result for these test cases. As I said before, different colors represent different shape of dependency. White nodes here are independent test cases. These test cases are not dependent to any other test case. You can execute them. You don't need to execute one test case before. They are quite independent. Gray node represent dependency class 1, which means these nodes are dependent to the independent test cases. There is no multiple dependency between them. They are single dependent. And black nodes here represent multiple dependency. In other words, the black node should be executed as a lost test cases. For getting pass answer for a black node, you need to get pass answer for every other nodes behind these nodes, every other test cases behind these test cases. So we monitored the result for test records for these 5 test cases. According to our claim, the black node should be executed as a lost test case. The red numbers here represent the order that testers did at Bombardier, and the blue nodes, blue numbers, are our suggestion for execution. So as you can see, the black nodes should be executed as a lost test cases, but they took these test cases as a test case 1 for execution, and they got pass answer for this test case when they got pass answer for every other test cases behind these test cases. So estimated time for execution for these 5 test cases is 5 hours by our methods. But it took 45 hours for execution. And the total saving time is 40 hours. But we need to consider that the process of detecting dependency takes time, creating this graph takes time, and this 40 hours is just execution hours. And we detect this dependency information with help of engineer and tester at Bombardier, and there's other reasons that they couldn't follow up this structure. So in case 2, we applied again our method in another finished project at Bombardier. This graph shows more than 100 test cases. One node represents one, and sometimes more than one test cases, just because there is overlap between test cases sometimes. And this problem is a multi-objective, multi-criteria optimization. We try to maximize detecting faults in the system, and at the same time, we try to minimize the testing effort. So we have two different objectives in this project. And we use TOPSIS technique. TOPSIS is a technique for multi-criteria decision making, and this technique is based on two ideal solutions: a positive ideal solution and a negative ideal solution. A positive ideal solution in this example would be a test case. You can assume the best scenario that you have. This test case is a very good test case, independent, the execution time is very high, the cost is very cheap, and this test case can cover more than one requirement. As the best scenario, maybe you haven't this magic test case in the reality, but you can assume it, you have it. And negative ideal solution is a worst case scenario. It's a very bad test case, quite dependent test case, requirement coverage is low, there is no chance to detect a fault by this test case, and execution time is very high. Every other test cases located between these two solutions. So what is your task? You need to propose a set of test cases which has a less distance to positive ideal solution, but at the same time, they need to have maximum distance with negative ideal solution. We used one indicator, fault failure rate, lambda, and you can find lambda, you can calculate lambda by the following formula: F, the number of failed test cases, divide to T, the total number of test cases. So lambda with our approach is more than lambda that happened in reality. We improved lambda, and in other words, we send a subset of test cases for execution. We don't claim that we detect more faults. We just send less number of test cases for execution, and we got same results. So we improved lambda. In case 3, we proposed 3 different versions of our prototype, and we measured the value return on investment to show how is economic beneficial to use our approach. And we translate the initial formula for return on investment to this formula: testing cost without our model minus testing cost with our model divide to total cost that we have in this model. And the total cost for our prototype is a sum of implementation costs, testing costs, and maintenance costs, and data collection costs. This figure represents the result. We used Monte Carlo simulation, and we analyzed for 6 years for one project what would happen if one industry would buy and use our prototype for test case selection and prioritization. Different colors here represent different version: automated, semi-automated, and manual version of our prototype. As you can see, the best decision right now is to use manual version, just because you have no implementation and no maintenance cost. But after 6 years, or starting in the 6 years, you have more gain by using automated version. We have 3 contributions which address 3 different research questions that I presented earlier. We provide a model of multi-criteria decision making. We redefine the initial problem in a fuzzy environment just to be relaxed. We haven't no sharp value. We solve this problem how you can use this method when you haven't sharp value in the system. In contribution 2, we propose a decision support system for test case selection and prioritization. And this decision support system is dynamic and online. And you can get a new decision per time after each execution. Contribution 3, answer research question 3, which is what is your gain, return on investment, if you're using and buying our prototype. As I said before, there's a positive value for 3 different versions. So your gain is positive. Like every other work, our work has some limitation as well. The most important thing is time consuming. This process takes time just because you need to compare and measure the effect of criteria on test cases. Right now is manually, but we are trying to develop our model and we are going to solve this problem with some with machine learning algorithm in the future. And the total time is high right now, but we are trying to solve this problem. This decision support system is just applicable for manual testing. We designed this problem for manual testing just because the initial problem was defined in manual testing, and we need to update and develop our model for other type of testing. The method is applicable when you have a large number but still finite set of test cases. If you are generating 1 million test cases per day, maybe it's not a good decision to use this prototype. We mapped our research work with Gorchek research methodology, which is a model for technology transfer and research in industry, just because we are working so close with different industry in Sweden. And we defined the initial problem with help of Bombardier. We find this problem as a hot topic in manual testing, test case selection and prioritization. For problem formulation, we have close collaboration with testers and engineers at Bombardier again, and we have meeting with them and we present our work. And for academic validation, we presented more than 5 papers in this area for this research, and we got different feedbacks from different conferences. Dynamic validation, we use different industrial case studies, and also for different phases for the project that we are working. We have different presentation and we present our result for different companies in Sweden. We try to release our solution by implementing our model. We have one version right now implemented by students, but we are working with it and we are trying to release as a product prototype in the future. I'm going to conclude my presentation with this slide. So first conclusion is the concept of multi-criteria test case selection and prioritization is applicable and can reduce the total required time for execution. You are going to get a earlier fault detection by using our prototypes. So still you can minimize the usage of testing resources. There's another optimization problem, and as a last contribution, we got a positive value for return on investment. For the future work, we are, as I said before, we are trying to implement and release our prototype for different companies, and we have an example screenshot of our prototype. This version that we have now as a tester, as an engineer, is very easy to use this prototype. You can just select with some linguistic variable the effect of the criteria, for example, execution time, requirement coverage, complexity, with some linguistic variable between very low and very high. And also, you can use different techniques for decision making, like AHP, TOPSIS, VCORE, and we are trying to develop our model in the future for different levels of testing. For example, right now we have this version for integration testing, but we are trying to have for regression testing, acceptance, and unit testing in the future. As a tester, you are able to record the result for test cases with pass or fail. So the initial algorithm would be updated per time when you record just the result for execution. And that's all, actually. Thank you. Thank you.